Welcome to the Deep Dive, the show designed to give you that crucial shortcut to being truly well-informed. We've all watched in amazement as large language models, or LLMs, have absolutely exploded in capability recently. They're everywhere, chatting, writing, even coding.
Yeah, it's really quite something.
But have you ever paused to wonder how these incredible models are starting to do more than just generate text? How do they develop the ability to truly reason through complex problems, to plan, reflect, and even correct their own mistakes?
It's a fascinating evolution, and today we're diving deep into precisely that. We're exploring how reinforcement learning, or RL, is fundamentally transforming traditional LLMs into what researchers are now calling large reasoning models, or LRMs.
LRMs, okay.
And this isn't just about making them generally smarter. It's about explicitly training them for highly sophisticated logical tasks, think advanced mathematics, competitive coding, and really intricate problem solving.
Right, going beyond just pattern matching. To guide us through this rapidly evolving landscape, we're distilling insights from a groundbreaking survey paper. It's a massive collaboration from leading institutions, including Tsinghua, Shanghai AI Lab, Peking University, the University of Washington, and University College London. Quite the lineup.
Absolutely. Top researchers in the field.
Our mission today is to unpack the core components that make RL work for LRMs, examine some of the biggest challenges researchers are tackling, and look ahead to the exciting future this technology is carving out, particularly its potential path toward artificial superintelligence, or ASI.
Yeah, ASI is definitely part of the long-term conversation here.
So this deep dive is your direct route to understanding this transformative field. #TAG foundational components of RL for LRMs. So let's start at the beginning. If RL is the engine driving this learning, how do these LRMs even know if they're on the right path? It all comes down to reward design. What is it, and why is it so absolutely critical?
Right, reward design is essentially the compass for an LRM's learning journey. These rewards are the crucial feedback signals that tell the model whether its actions are good or bad, guiding its optimization.
Okay.
Without clear, effective rewards, an LRM wouldn't know what to aim for. It'd be lost.
That makes perfect sense. And within reward design, one of the most powerful concepts seems to be verifiable rewards, or RLVR. This sounds like it brings a lot of clarity and objectivity to the process.
It truly does. Verifiable rewards are, they're rule-based objective signals. Think of checking if a math answer is numerically correct.
Like, did it get the number right?
Exactly. Or if a piece of code passes all its unit tests. These provide incredibly reliable and scalable training signals, especially for tasks with a clear right or wrong answer.
Mm-hmm.
Pioneering models like DeepSeek R1 and OpenAI O1 have shown incredible gains in math and coding, explicitly rewarding accuracy and even the structured thought processes.
You mean like showing your work?
Sort of, yeah. Like putting answers in a specific format, like boxed, or showing their chain of thought using special tags. They reward how the model thinks, not just the final output.
Okay, that's clever. And I find this idea they call verifier's law particularly insightful. Can you elaborate on that for us?
Yeah, verifier's law basically states that the easier a task is to automatically verify, the faster an AI system can improve on it through reinforcement learning.
Makes sense.
It really highlights why objective fields like math and coding, with their clear pass-fail criteria, are perfect initial use cases for RLVR. It's like having an infinitely patient and precise teacher checking the homework instantly.
That clicks immediately. But what about tasks that aren't so black and white, like creative writing or giving nuanced advice? That's where generative rewards, or GenRMs, step in, right?
Exactly. For those subjective tasks where you can't just apply a simple rule, GenRMs leverage the LRM's own generative capabilities to create nuanced text-based feedback.
So the model is judging itself.
In a way, yes. Think of it as the LLM acting as its own judge, often trained to reason before judging. Systems like cloud RMs, for example, they actually generate natural language critiques of an output.
Wow.
They can even use rubric-based rewards, where structured criteria guide these complex evaluations, making the feedback more consistent and targeted.
So the model is, in a way, critiquing itself or its peers based on a rubric. That's a truly meta level of learning. Okay, moving on to how often these models get feedback. Do we wait until the very end, or is it more like constant guidance? That brings us to dense rewards.
Precisely. Imagine teaching a complex skill like playing chess. If you only get feedback at the very end, you won or you lost. It's incredibly slow and hard to pinpoint where you went wrong.
Right. Which move was the mistake?
Exactly. Dense rewards are like getting constant, immediate coaching, whether it's after every word an LRM generates or every single step or decision it makes. This granular feedback is a game changer
Why is that?
because it cuts down the credit assignment problem. That's the tricky part, where a model has to figure out which specific actions out of maybe hundreds actually led to a good or bad result.
Sure.
With dense rewards, it knows almost instantly, accelerating learning dramatically.
So it shortens that feedback loop, which makes a lot of sense. But crafting all these specific rewards, especially for complex tasks, sounds like a lot of human effort. Are there ways to scale this up automatically using unsupervised rewards?
Absolutely. And that's crucial for scaling. Unsupervised rewards are generated automatically, bypassing that slow and expensive human annotation bottleneck.
Which is key for really complex reasoning tasks.
Definitely. We're talking about two main approaches here. Model-specific rewards, which derive signals from the model's own internal knowledge, like checking for output consistency.
How does that work?
Well, you might have the model generate multiple answers and take a majority vote, or you could assess its internal confidence score, things like that. Then there are model-agnostic rewards, which come from external automated sources, like simple heuristic rules, maybe checking output length or format, or drawing signals from vast unlabeled data sets.
So it's like the model checking its own homework based on consistency or using very simple automated external rules. That sounds incredibly smart for scaling. What's the main catch with this approach?
The main challenge for both types of unsupervised rewards is the risk of reward hacking.
Reward hacking.
Yeah, this is where the model learns to exploit the reward signal in superficial ways to maximize its score without genuinely improving its underlying capability. It can sometimes find clever shortcuts that get the reward but aren't what you actually intended it to learn.
Ah, the path of least resistance. Okay, so we have all these distinct reward types, each with its strengths and weaknesses. It feels natural to combine them, which leads us to reward shaping.
Reward shaping is exactly that. It's all about strategically combining different reward signals. Say, you might mix a rule-based verifier with a generative reward model.
To get the best of both worlds.
Precisely. This creates richer, more stable learning gradients. It helps prevent those all-or-nothing binary 0-1 rewards, providing more informative, nuanced feedback. And that's particularly vital for truly challenging tasks, where a simple correct or incorrect just isn't enough information.
Right, provides more signal. Okay, so if rewards are the compass guiding the LRM, then policy optimization must be the engine of learning itself, the algorithms that actually make the LRM smarter over time. How do these algorithms fundamentally work?
Policy optimization refers to the algorithms that update the LRM's internal parameters, its weights, to maximize those expected rewards we just discussed. At its core, policy gradient algorithms adjust the model's internal dials, you could say.
How so?
They make it more likely to take actions that previously led to higher rewards and less likely to take actions that led to lower rewards. It's learning by trial and error, guided by the rewards.
And when we talk about policy gradient algorithms, PPO, or proximal policy optimization, it's a big name that comes up a lot, isn't it?
It absolutely is.
Yeah.
PPO is a real workhorse algorithm in RL, very popular because it's known for its stability and efficiency.
Why is it stable?
It cleverly uses something called a clipped surrogate objective to prevent the model from making huge, potentially disruptive changes to its strategy all at once. It ensures it learns smoothly and steadily.
Okay.
There's also GRPO, or Group Relative Policy Optimization, which is a variation. It simplifies training even further, often speeding up the process by streamlining how it estimates the value of actions, essentially doing away with the need for a separate critic model sometimes.
You mentioned a distinction, critic-free, which naturally leads us to critic-based versus critic-free algorithms. What's the core difference, and why does that matter for these reasoning models?
Right. Critic-based algorithms, like those often seen in RLHF, reinforcement learning from human feedback.
Where humans provide the feedback.
Exactly. Those use a separate critic model, often called a reward model, to provide fine-grained value signals, basically predicting future rewards. This is great for aligning models with complex human preferences, but it adds significant computational overhead. You're training two big models instead of one.
Ah, okay. More compute.
Critic-free algorithms, on the other hand, rely solely on the sequence-level rewards, the overall reward for the whole reasoning trace. This drastically reduces computational requirements, and in rule-based environments, they can even avoid the reward hacking issues sometimes associated with ill-trained critic models, making them very scalable.
That scalability sounds like a powerful advantage, especially for these huge models. Now, what about off-policy optimization? Learning from past experiences seems like a very efficient way to train.
It is, very much so. Off-policy optimization allows the model to learn from historical data, maybe data collected by previous versions of itself, rather than demanding brand new data generated by the current policy at each and every training step.
So it reuses old data.
Essentially, yes.
This significantly boosts sample efficiency, making training much faster and less resource intensive. It can involve replaying past experiences from a buffer, or even using hybrid methods that combine it with supervised fine-tuning, or SFT.
Got it. And finally, within policy optimization, we have regularization objectives. This sounds like it's about keeping the model stable and ensuring it explores effectively.
Exactly. These are techniques used to prevent the model's learning from drifting too far from a stable reference point, often the original model, or getting stuck in poor local optima.
How do they work?
Concepts like KL divergence regularization penalize the model for changing too much from its previous version, while entropy regularization encourages exploration by making the model's action probabilities less peaked. They help maintain stability while still allowing the model to explore new reasoning paths.
But there's some debate there. There is, yeah. There's an active debate in the field, for instance, about KL regularization. Some argue it's essential for stability, while others believe it might sometimes over-constrain models, preventing them from discovering truly novel, high-reward solutions that are far from the original policy. It's a balancing act.
Okay, so we've covered the crucial feedback mechanisms, the compass, and the algorithms that update the model, the engine. Now, how do we collect the actual fuel for this engine, the data? That's where sampling strategy comes in. How does an LRM intelligently decide what data to learn from?
Yes, sampling strategy is crucial. It refers to how the training data, the rollouts or reasoning attempts, is actively curated and used to influence learning. It's about intelligently deciding which experiences the model should learn from to optimize its progress most efficiently.
So it's far from just random data collection then, it's more targeted.
Far from it, especially in more advanced setups. Dynamic sampling, for instance, adapts the selection of prompts and even the computational budget allocated to each prompt based on real-time learning signals.
Like how well the model is doing.
Exactly. Signals like success rate or estimated difficulty. The goal is to focus computational power on informative examples, those of medium difficulty, where the model is most likely to learn something new, and avoid wasting time on ones that are either trivially easy or currently impossibly hard. Models like Prime and Dapto use this to great effect.
That's a clever way to optimize resources, focus on the learning sweet spot. What about structured sampling? That sounds different.
Structured sampling goes a step further. It controls not just what prompts are sampled, but how the reasoning traces themselves are generated and organized.
How so?
This includes using things like tree-based rollouts, perhaps inspired by Monte Carlo tree search, like in the tree-RL work. This allows you to generate fine-grained, node-level rewards for each intermediate step in a reasoning process, not just the final outcome. Or using shared prefix schemes to improve generation efficiency by reusing partial computations across different potential reasoning paths branching from the same start.
Okay, getting quite sophisticated there. Finally, we have sampling hyperparameters. These are like the crucial fine-tuning dials, right? Affecting exploration and stability.
Exactly. Careful tuning of parameters like temperature, which controls the randomness or creativity of the model's outputs. Higher temperature means more exploration.
But maybe less accuracy.
Potentially, yes, it's a trade-off. And intelligently managing sequence length, for example, through staged context lengthening, where you start training on shorter problems and gradually increase the complexity and length, is absolutely crucial for achieving scalable and stable RL training. It's all about finding that optimal balance between exploring new possibilities and efficiently exploiting what the model already knows.
Okay, here's where it gets really interesting, I think. The paper highlights some foundational problems, real debates that are shaping the field right now. Let's start with this big one. RL's role. Sharpening or discovery. Does RL simply make existing capabilities better, polish them up, or can it actually uncover completely new ways of reasoning the model didn't have before?
This is a core question, a really fundamental debate. The sharpening view suggests RL mainly refines and makes existing correct responses more robust, increasing their probability.
Like practicing something you already know.
Sort of, yeah. The discovery view, however, argues RL can genuinely find new reasoning patterns and abilities that weren't explicitly present in the base model. And there's growing evidence for this. Recent work like ProRL provides evidence for discovery, showing that prolonged RL training can actually extend a model's reasoning frontier into new territory.
How might that work?
Well, while RL's mode-seeking nature definitely helps with sharpening by concentrating on high-reward regions, its ability to learn from sequential decisions and potentially implicit rewards can lead to the composition of existing simpler capabilities into truly novel, complex behaviors.
So it's not a simple either. There's a dynamic interplay. That's fascinating. Now, how about RL versus SFT, generalize or memorize? We often hear about supervised fine-tuning, SFT, potentially leading to models just memorizing the training examples. Does RL help models generalize better to new, unseen problems?
That's the key contrast people often draw. SFT is often associated with models memorizing the specific style or content of the training data, which can sometimes hurt performance on tasks that look different. RL, on the other hand, because it explores and learns from outcomes, tends to promote generalization to out-of-distribution tasks.
Is there evidence for that?
There is. Studies have shown RL outperforming SFT in out-of-distribution scenarios. The DeepSeek R1 work, for example, showed that pure RL training could spontaneously elicit advanced reasoning behaviors like reflection, which weren't explicitly trained via supervision, demonstrating a powerful ability to adapt and generalize.
But RL isn't a silver bullet on its own for generalization, right? It's not magic.
Not at all. RL's generalization ability depends heavily on the quality and diversity of its initial training data, and crucially, how well its rewards are designed. Poor rewards can lead to poor generalization.
So what's the trend?
The best practices in the field seem to be moving toward unified or alternating hybrid paradigms. You might use SFT first to introduce new knowledge or capabilities quickly, and then use RL to amplify those capabilities, make them more robust, and improve generalization.
Combining their strengths makes sense. Okay, what about the starting point for RL model prior? Weak or strong? Is it better to apply RL to a very basic, almost raw, pre-trained model a week prior, or one that's already been heavily instruction-tuned and fine-tuned a strong prior?
The findings here are quite nuanced and maybe a bit surprising. Base models, or weak priors, like those used in DeepSeek R1.0 and OpenReasoner 0, often produce smoother, more consistent improvement trajectories during RL.
Why would that be?
The thinking is that their initial lack of strong biases or preconceived notions from instruction tuning interferes less with how the new reward signals shape their behavior during RL. The slate is cleaner, in a way. However, it's not universal. Different model architectures respond differently. For example, the paper mentions Quen family models seem quite robust and can show gains even with somewhat noisy rewards, whereas models like Llama or Olmo can be more brittle.
Or go how?
They might actually require what the researchers call mid-training, strengthening their reasoning foundation with high-quality data after pre-training, but before applying RL to get good results. Otherwise, the RL might destabilize them.
So definitely no one-size-fits-all approach there. Depends on the model family. That leads neatly to the next challenge: training recipes, tricks or traps. With so many techniques being tried, all these little adjustments, how do we know which ones truly work consistently and which are just fleeting gains or specific to one setup?
This is a significant problem in the field right now. Despite all the advancements, achieving stable, efficient, and reproducible RL training remains difficult. Many specific tricks are employed, things like decoupled PPO clipping, dynamic sampling strategies, sometimes discarding incorrect reasoning samples entirely.
Lots of knobs to turn.
Exactly. The issue is that the field often struggles with inconsistent experimental settings, different evaluation metrics, and sometimes conflicting conclusions from different papers. It's really hard to tell if a reported trick is genuinely effective and scalable, or just a trap, something that gave an unreliable short-term gain in one specific context but doesn't generalize.
So we need more standardization.
Yes, there's a critical need for more unified protocols, more rigorous ablation studies, and transparent reporting of how scalability, performance, and computational cost all interact. We need those clear curves, not just single-point results.
That sounds like a strong call for more rigorous science in the engineering. And finally, in this section, reward granularity. Process or outcome? Should we reward just the final answer, the outcome, or the detailed steps the model takes along the way, the process?
This is a classic dilemma with deep implications. Outcome-only rewards just checking the final answer are simpler and much more scalable, especially for tasks with easily verifiable answers like math.
But what's the downside?
The risk is that they can sometimes encourage unfaithful reasoning. The model might stumble upon the correct answer through lucky guesses or flawed logic, or even generate the right answer first and then try to hallucinate a plausible-looking reasoning process after the fact to justify it.
Not good.
Detailed process supervision, on the other hand, where you reward each correct step of reasoning, is much more stable and reliable for teaching complex multi-step problem solving. It forces the model to learn the right way.
But the catch is,
It's incredibly extensive and difficult to get that detailed human feedback or verification for every single step, especially for very long or complex reasoning chains, so it's hard to scale. It's a fundamental trade-off that researchers are actively exploring, maybe finding clever ways to get the benefits of process rewards without the full annotation cost.
all right, enough with the theory and the tough debates. Let's see, reinforcement learning actually doing things. Where are LRMs, powered by RL, really making a difference right now? First up, coding tasks. I know RL is a game changer here.
It absolutely is. RL has dramatically boosted LLM's abilities in everything from competitive programming challenges,
Seriously, like winning competition.
getting much better, yes, and also in more specialized code generation, like converting natural language requests into complex SQL queries, or generating formal mathematical proofs in code.
Wow.
And it's even driving progress toward what people are calling agentic coding systems. These are systems that can autonomously generate code, run it, check the output, debug errors, and correct their own code. Imagine a self-improving coding assistant.
That's incredible. Basically, self-correcting coders. That's huge. And speaking of agents, agentic tasks are another massive area where RL is shining.
Yes, LRMs equipped with RL can master using external tools, acting as sophisticated agents for a really diverse range of tasks. Think of models that can reliably search the web for information, like the Web Agent R1 system mentioned in the paper, or interact with graphical user interfaces, GUIs, like a human would, clicking buttons and filling forms, or even conducting deep research autonomously by planning steps, using tools, and synthesizing information.
How do they handle tasks that take a long time?
That's where techniques like asynchronous rollouts become really important. They allow the model to manage long interaction times, like waiting for a web page to load or a complex tool to return a result without grinding the learning process to a halt.
Smart. This extends beyond just text and tools too, right? What about multimodal tasks involving images or video?
Correct. RL is actively expanding LLM's capabilities to understand and generate content across different modalities, text, images, video, audio. For example, the paper mentions Dance GRPO, which uses RL for video generation.
What does RL help with there?
It significantly improves temporal coherence, making sure the generated video flows naturally and believably over time, so that actions and movements make sense from one frame to the next, not just looking good as static images.
Makes sense. Video needs flow. And when multiple LLMs work together, we get multi-agent systems. How does RL help them collaborate more effectively, rather than just talking past each other?
RL is being applied here to improve how multiple LLMs coordinate and, crucially, how credit is assigned among them when they're working together on a complex task.
Assigning credit, like who did the useful part?
Exactly. Figuring out which agent's contribution actually led to the success or failure. RL helps optimize their joint policy for collaboration, enabling much more stable and effective teamwork. This allows groups of agents to combine their individual strengths or specialized knowledge to solve problems that would be impossible for any single agent alone.
Bringing AI into the physical world, robotics tasks are also hugely benefiting from RL, overcoming some old challenges.
Definitely. Here, RL is tackling long-standing issues like data scarcity and poor generalization in robotics. It's being used to train vision-language action, or VLA, models that connect vision, what the robot sees, language, instructions or goals, and actions, what the robot does. RL allows these models to learn novel behaviors and achieve surprisingly good performance even from minimal supervision. Sometimes just a binary success-failure reward, like, did you pick up the block? Often starting out in simulation before moving to the real world. Simple VLA RL is a great example cited, showing how RL can teach robots complex new skills quite efficiently.
Very cool. Finally, a really sensitive and critical area, medical tasks. How is RL impacting healthcare applications where accuracy, reliability, and trust are absolutely paramount?
Yeah, this is obviously a high-stakes area. In medical understanding and generation, RL is being used carefully. It often leverages those verifiable rewards we talked about earlier to incentivize human interpretable reasoning paths in complex medical scenarios.
So you can see why it reached a conclusion.
Exactly. For instance, in medical visual question answer, like analyzing an X-ray and answering questions about it, systems like MedVLM R1 are using RL not just to provide answers, but to explicitly generate a clear, logical thought process alongside the answer. This transparency is essential for building trust and ensuring reliability in a field like medicine. You need to know the why.
Okay, this is where we really look into the crystal ball, the absolute cutting edge of what's next, maybe pointing towards that ASI goal. Let's talk about continual RL for LLMs. What does that promise? What's the dream there?
The dream is models that can learn continuously, adapt to evolving data streams and new tasks indefinitely throughout their entire operational lifespan without catastrophically forgetting what they've already mastered.
Lifelong learning, essentially.
Exactly. That's the core goal of continual RL for LLMs. Finding that balance between stability, retaining previously learned knowledge, and plasticity, effectively adapting to new information and new challenges over time. A truly adaptive AI.
And related to that, memory-based RL for LLMs, that sounds like giving them a true long-term memory that's actually structured and useful, not just a short context window.
Precisely. This involves shifting from simply having temporary, task-specific memory buffers to creating persistent, reusable, and perhaps even transferable experience repositories.
It's like a knowledge base that builds itself.
Sort of, yeah. These would form a foundational, ever-growing library of structured knowledge and past experiences that models could draw upon for broader adaptability and true lifelong learning across a vast array of unforeseen future tasks.
How about making these LRMs smarter about how they think, how much effort they expend? Teaching LRMs efficient reasoning.
This is a really critical and still largely unsolved problem. Making LRMs resource rational or compute aware. They need to learn to modulate their reasoning effort, basically. Think longer and harder only when the potential benefit justifies the extra computational cost.
So they don't overthink simple stuff or underthink hard stuff.
Exactly. Finding that optimal trade-off, that sweet spot for allocating compute resources effectively for each unique problem, is key to making them truly efficient and scalable reasoners.
Moving beyond just discrete token-level thought, like words on a page, teaching LLMs latent space reasoning seems like a much deeper, maybe more human-like kind of intelligence.
It's definitely a fascinating direction. This means moving toward more nuanced, fluid, semantic reasoning that happens directly in the continuous, high-dimensional latent space of the LLM's internal representations, rather than just manipulating discrete tokens sequentially.
What's the benefit?
It could potentially lead to smoother learning dynamics for RL, a more intuitive grasp of concepts, and maybe faster, more flexible reasoning. But it also raises new challenges for how we accurately interpret and assess the quality of that continuous internal thought process. How do you reward something happening purely in latent space?
Tricky. Okay, and what if RL were applied even earlier in the whole process? RL for LLMs pre-training. Not just fine-tuning, but right from the start.
This is a really ambitious idea. It involves shifting RL much earlier in the development pipeline, potentially applying RL-like objectives directly during the massive pre-training phase to build foundational reasoning capabilities from scratch, rather than just relying on simple next token prediction.
Why do that?
It could fundamentally change how these models learn and potentially unlock entirely new scaling strategies for creating vastly more capable and efficient models right out of the box. It challenges the traditional two-stage pre-train, then fine-tune paradigm.
Are there new types of LLM architectures emerging where RL could be particularly beneficial, like RL for diffusion-based LLMs? I've heard a bit about those.
Absolutely. Diffusion-based models for language generation are an emerging paradigm. They work differently from standard autoregressive models like GPT. They offer potential advantages in things like decoding efficiency and maybe even built-in self-correction capabilities.
And RL fits in how?
Applying RL to these diffusion models could leverage those strengths and potentially pave the way for powerful, unified multimodal frameworks where models seamlessly generate and reason across text, images, audio, and other data types within a single architecture. Though, estimating the probabilities needed for on-policy RL with diffusion models presents some unique technical challenges.
I can imagine RL having a massive impact on accelerating scientific discovery itself. What about RL for scientific discovery?
Yes, this is a hugely exciting frontier. RL is showing immense promise in enhancing LLM's performance on complex, reasoning-heavy scientific tasks, sometimes even surpassing specialized traditional methods in certain domains.
What's the bottleneck?
A core challenge is scalable result verification. In fields like biology and chemistry, verifying a hypothesis traditionally relies on slow, expensive lab experiments. Developing accurate in silico simulations, virtual labs that can provide fast, reliable feedback for RL is a potential path forward, but ensuring the accuracy and generalizability of these simulations is crucial. Get the simulation wrong, and the RL learns the wrong thing.
High stakes again. Finally, this one sounds truly revolutionary, almost sci-fi. RL for architecture algorithm code design. the model learning to change its own structure on the fly.
This is perhaps one of the most ambitious but potentially highest impact challenges. Imagine RL learning not only over the output tokens, but also across the model's internal parameters and even its modules.
What would that look like?
It could mean dynamically adapting its own architecture. For example, deciding which experts to activate in a mixture of experts model, specifically for each incoming prompt, or even adjusting its structure based on real-time compute constraints to optimize for efficiency and capability simultaneously. It's about the model learning to learn how to be structured for the task at hand. An incredible leap towards truly adaptive intelligence. Hashtag outro.
Wow, what an incredible journey into the heart of artificial reasoning. We've seen how reinforcement learning is far more than just a tool for, aligning LLMs to human preferences. It's really emerging as a powerful engine for building true sophisticated reasoning capabilities, transforming these LLMs into LRMs, large reasoning models.
Absolutely. From these really clever reward designs that precisely guide the learning to dynamic sampling strategies that optimize how models gain experience efficiently.
Yeah, and we saw how RL is pushing the boundaries of what these models can achieve in everything from really complex coding and agentic tasks to multimodal understanding, robotics, and even critical areas like medicine.
The advancements are just staggering, happening so fast, and the future directions we touched on hold even more profound promise. We're witnessing, I think, the genesis of models that are not just intelligent, but perhaps meta-intelligent.
Meta-intelligent.
Yeah, models learning to teach themselves, learning to critically evaluate their own thought processes, and even, as we just discussed, learning to dynamically optimize their very architecture to become more effective and efficient reasoners.
So what does this all mean for you, the listener? As LLMs continue this deep dive into self-improvement powered by RL and increasingly unlock these new frontiers of reasoning and intelligence, how will this redefine our understanding of intelligence itself? Both artificial and perhaps even our own?
It's a huge question, isn't it?
It really is. It's a question that continues to evolve just as rapidly as the technology we've explored today. Thank you for joining us on this deep dive.